Hello, everyone. My name is Olivia Harlow, and I'm a member of the 2025 Relate cohort. And today I'm going to be talking to you about the immune system and specifically about a T cell type called a resident memory T cell. So, to introduce you all to the immune system, it is a network of organs and tissues that aim to protect the body against things like infection and cancer. The immune system essentially encompasses our entire body, in part due to the lymphatic system, which is kind of has these anchor points known as lymph nodes. And we'll get into a second why lymph nodes are really critical. The immune system helps protect against foreign invaders to the body that can cause infection. Think things like bacteria, viruses, and parasites. And a quick question before we move on, what are some examples of pathogens that you can think of? So in today's day and age, a really common infection that is, I think, on the forefront of everyone's mind is SARS-CoV-2, which causes COVID. But there's a whole lot of other infection or pathogens out there that can cause infection. Think things like Staph aureus, which causes staph infections, influenza, which causes the flu, and a whole lot of other ones, which is why it's important that our immune system is functioning well, because we are essentially exposed to pathogens every single day. So now I want to get into a metaphor to introduce how the immune system functions on a basic level. So in this example, we're going to be thinking about our body and our immune system as a fortress and pathogens as zombies. So in the fortress, we have people that sit at the wall in order to assess whether or not zombies have broken through the wall and can help fight against them. But the fortress is also just functioning on a day-to-day level. And so we have homes back here, and within these homes are somebody that we're going to be introducing a little in a second as a coordinator. So, oh no, the zombies have broken through. So the people at the wall are now able to start fighting against the zombies, but they might not be using the best weapons, and there's not enough of them to really fight off the zombies as much as we would want to. So to help fix this, we have to wake up this coordinator. And so we have a messenger that gets sent from the wall out to the homes in order to wake up the coordinator. So now that our coordinator is up and at 'em, back out at the wall, he now is able to help rally more people in order to help fight off against the zombies. And he's also able to communicate to the people at the wall to use more efficient weapons rather than guitars and toilet blenders, metal weapons that are a lot more effective. So now that the people have fought off the zombies, the wall actually is able to be repaired and things in the fortress kind of go back to baseline. We have people sitting at the wall, again, assessing, making sure that there's no zombies breaking through. But something that is changed is that the coordinator is now stationed a lot closer to the wall in case that the zombies break back through that part of the wall again. If he's closer, he's able to respond a lot faster. And our immune system kind of works in a really similar way. So, in this example, we have a barrier, which is known as a barrier tissue. These are things like your skin, your gut, and your lungs in yourself. And at your barrier tissues sit something called innate immune cells. And innate immune cells are those people that sit at the wall. They're able to watch over the barrier and make sure that nothing breaks through. And if any pathogen breaks through, they're able to sound the alarm and start and get that coordinator awake. So in our lymph nodes, which, as I mentioned before, are really critical, these house something called adaptive immune cells. And specifically, we're going to be talking about a T cell, which is a type of adaptive immune cell that lives in your lymph nodes. And these lymph nodes or these T cells in your lymph nodes are unactivated currently. They're naive. They are sitting there snoozing. And so in the case of a pathogen breaking through, they need to be activated. So pathogen has broken through. Now our innate immune cells are starting to step up. They're starting to fight against the pathogens, but there's just too many of them, and they're not, using the most coordinated methods. So a messenger cell has gone and woken up our T cells, activated our T cells in our lymph nodes, and called them out to the barrier tissue in order to start communicating with our innate immune cells in order to have them kill the pathogen more effectively, as well as bring in and more more innate immune cells to the site of the infection in order to protect against the pathogens. So now that the pathogens have been eliminated from the body, um, it's able to undergo wound repair, and everything's back to baseline or back to homeostasis. However, our T cells have actually stayed out in the tissue, and have formed something called memory. And what is memory? So we just mentioned what a primary response looks like. That's the first time that our T helper cells that are located in our lymph nodes are seeing their pathogen. That's when that messenger goes out and talks to them. And that's the first time that you're infected. But should you get reinfected again, there's something called a secondary response. So, as I mentioned, this is the next time you're infected with the same or a similar pathogen. And essentially, your memory helper T cells are able to see their pathogen again and respond both faster and stronger. And one of the T cell types, the one that I kind of demonstrated earlier, which sits in that barrier tissue after the infection's cleared, is called a resident memory T cell. And these resident memory T cells employ really similar methods in order to protect against repeated infections. They coordinate an immune response both faster and more powerfully during a reinfection than during a first infection. And if we're putting this in context, how helper TRM cells are important to protect us, if you think about it, during a single semester, it's probably pretty often that you're going to get one cold, but it's not super common that you're going to get more than one cold. And this is in part due to your helper TRMs because they're going to sit in the areas of your body that you got infected in, so your upper respiratory tracts or your lungs, and they're going to recognize similar viruses that cause common colds should you come in contact with them. So hopefully this means that you only get sick once, maybe twice a semester instead of a lot because you're technically seeing these viruses a lot because they're all around you in your class, in your bus. So because these helper TRM cells are not only able to protect us in the sites that we are getting infected at, but also able to see related pathogens and not just the same pathogen, can we use these TRM cells as a preventative measure against infection? So, how do we prevent against infections? We use vaccines. Vaccines are specifically developed so that our immune system recognizes part of a pathogen and then develops immune memory against that part of a pathogen. However, if you think about it, you really only get your vaccines in your arm for the most part, and you're not going to be seeing a whole lot of infections in your arms. So most current vaccines don't generate TRM cells. And we believe in our lab, because of the reasons that I've mentioned before, that targeting TRM cells through vaccination can help lead to more broadly protective vaccines in the future. So my dissertation work specifically is researching what cues helper TRM cells need to form. And this can potentially lead to a vaccine that is able to form TRMs in the site that they're going to see an infection, and help more broadly prevent against related infections. So some takeaways. We learned that the immune system fights against pathogens. We also learned that the helper response or the immune response consists of many components, and T helper cells help coordinate that immune response. We also noted that immune memory allows for both faster and more robust immune responses. And these helper TRM cells play a really critical role in this because they stay in the tissue to provide a faster response in that site. So lastly, we learned that vaccines promote immune memory, and we also learned that we believe that targeting TRM cells through vaccination can potentially improve immune responses to infection. All right, that's all for me today. Thank you so much for listening. See you later.